Yeah. Let's see how many of you can get the connection. Okay, good. None is there. Two people have come. So, anybody else getting the connection is a problem. It's okay. We'll wait for 5 minutes. Yeah, Padma. Padma is there. Who is 720 number? 720. Who is that? Seven two zero. So 3 people have come. Are they trying or? Okay, we'll continue. So 3 people. Should I wait for a few minutes more? Okay, we'll continue. Now see here. We have 3 bonds here. These 3 are sigma bonds. Remember this? These 3 are sigma bonds. Sigma bonds. Sigma bond. And sigma bond. Okay, and this is in a unhybridized p orbital, and that is what we have shown here. Now these sigma bonds are in a perpendicular plane. So I will draw this with in a perpendicular way. I have to draw this in a perpendicular fashion. Okay. So let me draw this bond. This is a bonding orbital. Remember this. This is in a perpendicular plane with the hydrogen. Okay, I will blacken this. Why I'm blackening it? Because it is pointing towards you. Okay, now you have one orbital here. This is in the plane. I will draw like this in the plane. Okay, and now you have one orbital behind this. One orbital behind this. See here. I will put in a dotted line. I hope you get the picture. Right? So this is now, so you have 3 hydrogens here. Right? Now we will consider only those, just consider one. You have 2 electrons here. Remember this. So this contains 2 electrons. This contains 2 electrons. And this also contains 2 electrons. Okay? All these 6 electrons of these bonds. So the 6 electrons of this bond, I'll repeatedly write it. These 6 electrons are in a perpendicular plane to this, are in orbitals which are perpendicular to the plane of these 3. And therefore, this electron will never enter into this orbital. This electron will never enter into this orbital. See here, if you have one orbital like this and an orbital like this, they can never interact. this interaction is never possible. Is that clear to you? If two orbitals have to interact, they should be either this way, see this, they can interact. You can draw these pictures. Draw these pictures in your paper, in your book. This can interact. Similarly, this interaction is also possible. They can interact. Put it right here. But this is wrong. Similarly, this also is wrong. Suppose I have an orbital like this. I have s orbital here and something in this direction. This interaction not possible. In two different planes, if they have to interact, they should interact here. Okay. So interaction will never come to the node. This is a node. Well, you don't have, this is node. Node. No electron density here. And therefore, you cannot interact here. Not possible. Okay. So draw these figures. So this is s orbital. S orbital. S orbital of hydrogen. And this is the p orbital of carbon. So this interaction is allowed, this is not allowed. Okay, because it's a node here. So these are the types of interactions. So therefore, there will be no interaction between this p orbital, this odd electron, that is orbital containing one electron. Oh, how did I put two electrons here? This orbital containing one electron will never interact with this one. Okay, so there will be no interaction here. No interaction. I'll write it here. No interaction. No interaction means electron flow. Electron will never, no electron flow. Why? Because they are mutually perpendicular. No electron flow. Because mutually perpendicular. Mutually perpendicular. This is the sign of perpendicular. You must be knowing this. Okay? So when the orbitals are in mutually perpendicular, they will not interact. Therefore, these bonds will not interact with this electron. Now let me write another one. Let us write, this is methyl. Now let us write it, write ethyl molecule. Write the ethyl one. See here. I have got a CH2, one orbital here. Okay, let me write the ethyl. See here. This is one carbon. This is one hydrogen. This is another. Oh, okay. This is in the plane of the board with one H. This is in the plane of the board with the next carbon, CH3, C. Oh, no, one second. Drawing this figure is very tricky. This is a sp3 hybridized carbon. Note that. Now I have to draw this in a tetrahedral fashion. Here is the next one behind. Okay, and here is the next one. See H bond. H. This is H. This also is H. See this. Draw the figures in the same fashion in your book. Okay. Now here is one carbon. Now I have not finished this carbon. Let me finish this carbon very carefully. So the drawing is very important. The way you draw it. Take your time to draw. Should be a very neat figure. Let's see here. Now, so you have one carbon, one methyl group, and now you have two hydrogens here. Two hydrogens. So one hydrogen I have drawn here. This is one hydrogen. Okay, that is in the plane. In the plane. Or we should okay, do one thing. We'll put this in the this is in the plane, and this one in a perpendicular plane. So we will put this, darken this. Okay. Now you have one more hydrogen, one more CH bond behind this. I'll explain to you once. This is the same as this one. These two are the same. C H H C H H and H. Now you have this one, in which there is one electron. So let me draw that down. Okay, the picture is very clear. See here. See here. These are perpendicular, mutually perpendicular. These are mutually perpendicular. And these are mutually perpendicular. Are you able to see it? Okay, let us draw it here. Try to understand very clearly. Mutually perpendicular. Write it here. You will, when you look at it again, you can very easily clearly understand this. See here. These are mutually perpendicular. Now, these two are mutually perpendicular. Mutually perpendicular. And what about these two? See here, backside. That is also mutually perpendicular. Mutually perpendicular. What is the meaning of that? They will not interact. There is one electron here. So this will not interact with this hydrogen, with this. This is the same case as here. We have already described it. Then ಮೊದಲು just 1 second. Just 1 minute. Okay, now see here. So there will be no interaction between these mutually perpendicular bonds. That is, this electron will not enter into this orbital, or this orbital. But see this one, see? Now I will draw it separately here. I'll draw it separately. See this. Only that bond I am drawing separately. H. and this orbital. See, they are parallel to each other. They're almost parallel to each other, right? Now, remember this. This is a sigma bond. You can rotate this. This will be always rotating. When around this carbon, if this carbon is getting rotated, now any particular time, all these can, one of these can align with this orbital. Okay, one of these can align with this orbital in this fashion. You're rotating it always. 360 degrees you can rotate it because C is single bond. So there will be interaction with this. So allowed interaction. Allowed interaction. They can form a bond. That is, the meaning is this orbital can form a pi bond with this orbital, and the hydrogen can free itself from here. That is, see here, this orbital can form a pi bond. And what will happen? See this, the result is this one. See, if it forms a pi bond here, see that, if it forms a pi bond here, this H will get separated, and these two bonds will slightly bend to upper side to become planar. See here. See, double bond. See, it's forming a pi bond. Double bond. Now, what happens to hydrogen? Hydrogen hangs around here, doesn't leave. H plus. And see here, carbon, carbon, hydrogen, hydrogen. Is it clear? See that? See that? Now, instead of this hydrogen also can participate. This hydrogen also can participate. So, what is the net effect? Sorry, it's not a, it's not the plus charge here. It's a radical. One second. One second. One second. Let me redraw this. One second. Yeah. What I should have drawn is this way. One second. The formation of this, I will destroy it in a homoetic fashion. One second. Yes. Now see, one electron and this orbital electron. See here, electron in this orbital. Now, see this. This forms undergo a homoetic fusion, and this also participates here. Draw correctly. Now, what will happen to this? This electron will flow to the hydrogen atom. So, this hydrogen gets that all electron. So, effectively, what has happened? The electron in this orbital has spread to this hydrogen. Okay, the electron in this orbital has spread. It is delocalized. We will use the word delocalized. Delocalized. The electron has got delocalized to this hydrogen. You can write the same thing with this hydrogen also. Also this hydrogen. That means if you have one methyl group attached to the carbon, when you have one methyl group attached to this carbon, you can write 1, 2, 3. Okay? And one original one. So 4 hyperconjugated structures. 4 hyperconjugated structures. Hyperconjugated structures. Suppose you have 2 methyl groups. Okay, so 1 methyl group, 4 hyperconjugated structures. If you have 2 methyl groups like this on the same carbon, here I have put only 1 methyl group. See, this is 1 methyl group. If I have got 2 methyl groups, how many hyperconjugated structures will be there? Suppose you have 3 methyl groups. Again, how many hyperconjugated structures will be there? You can find out. Clear? So draw all these figures. For the secondary, this is primary, secondary, and tertiary. And that will explain. Now, once you do this, now tell me, what is the order of, what is the order of stability? Order of stability. What is the order of stability when we consider hyperconjugation? When we consider hyperconjugative effect. Please write down whatever I am drawing on the board. Hyperconjugative effect. What is the order of stability? Okay, is it the same as that of inductive effect or is it in the reverse fashion? Okay, so find out that. We will discuss the remaining part tomorrow. Okay, thank you.